Right, so this is lecture number 3. We'll do a quick recap of lecture number 2. So in the previous lecture, we talked about some fluid mechanics that we have learned in our school times. We talked about Pascal's law, U-tubes, energy conservation law, so a mix of statics and dynamics. We talked about buoyancy, the idea of compressibility and incompressible fluids. We talked about the idea of viscosity as we have understood it in the past. We talked about the idea of ideal fluids or inviscid fluids that do not have any viscosity. So an ideal fluid is a fluid that flows freely without any resistance. Then we talked about steady flow, some very basic ideas of rotationality. And mind you, we'll discuss these things in detail in this course. It's just a quick recall of these terms that you have heard in the school time. So we'll keep repeating these terms and then build over that. Then we talked about conservation of mass, and then so this is what we had learned in the past, and then some new ideas. We talked about the idea of the continuum concept. So although the world, the universe is discrete in nature, in the sense of filling the space with atoms, mostly the space is empty. It's only at discrete places you will see some peak in masses. But still we can consider this continuum concept where the volumes that we consider are such that they have such a large number of molecules that we can define point properties as an average of the property over some small volume. And since we are dealing with scales which are much larger than this 10 micrometer, for example, this is an example, okay, 10 micrometers. Since we're dealing with large scales in general, then we have enough number of molecules in the smallest of the smallest scales that we can define some spatial averaging. And again, our whole theory of fluid mechanics that we'll discuss in this course is based on this concept of continuum being valid. If you're talking about rarefied gases or vacuums and so on, in those or outer space, for example, in that case, these ideas of fluid mechanics will start failing because the Knudsen number will become much larger in that case. Right, and then we talked about the contrast between theory and experiments, and we also talked about how they complement each other, where we start from one, then perform the experimentation, and then we evolve or learn further from there. Okay, so this was some basic ideas, and this was very general, very qualitatively we discussed these things. We'll continue with our discussion on these basic ideas today before we start going deep into the quantification of concepts. Right, so I had uploaded the reading assignment. That was chapter number 1 from the book, and I'd also given you a couple of problems to practice. So please practice the problems. I mean, learning is going to happen if you practice working through them. And as we discussed that the problems are not supplementary in nature, they're complementary. So you will learn from the problems as well. Right, so let's start with the next idea for today. That's called fluids. So what are fluids? We've been talking about fluids and fluid mechanics, but what exactly is a fluid? How do you define a fluid? Okay, so fluids are materials which cannot stay stationary under shear load. Okay, so shear load we understand. So let's say this is a solid to start with, for example, and if I apply a force which is tangential to the top surface, we call it shear force. Okay, normal force is one that is perpendicular to the surface, and shear is tangential to the surface. So if I apply a shear force, and what we expect in this case is the solid shape to change. It becomes something like this. So we say that there's an angle change, and the solid shape will change, and then it will stop changing its shape after some time, depending on the elastic properties, the stiffness of the solid. And then it will stop. Okay, so this we say that F shear results in an angle change. Now for fluids, if you apply a shear change, then what will happen is, as time progresses, this angle change that you get will keep increasing. So what we are saying is that F shear will result in a d theta by dt. So if you keep applying this F shear, then the fluid angle, that is this theta, will keep changing. Fluid will flow. So this fluid, the solid was stationary under shear load. Changed the angle, but after that it became stationary. But the fluid cannot do that. Fluid will keep flowing. Its theta will keep changing. So a shear force in a fluid will result in a continuous change in the theta angle. Okay. So let's write that definition. So they cannot stay stationary with an A under shear load. Is that clear? It's a very important concept. I mean, that is what exactly a fluid is, nothing else. So if you have a fluid, a different kind of fluid that can resist and that will stop flowing if a continuous shear force is acting, then technically that is not a fluid by definition. Now, of course, I mean, how much of a change we'll get, that's also very important, right? So if a solid, a shear force results in a theta change, then the amount of theta you get for a given shear force, that depends on the stiffness. So for a more stiffer, for a stiffer solid, you'll get a smaller theta change. For a very non-stiff solid, you'll get a large theta change. Similarly, the amount of d theta by dt you get will depend on the viscosity of the solid. I'll call it theta dot. So it depends on the viscosity mu of the fluid. All right. And mind you, fluids can take compressive forces, and they do take that. We know that. I mean, under the ocean, for example, there is a lot of compressive force acting because of the pressure, hydrostatic pressure. So fluids can take compressive forces, and then what I mean by taking compressive forces is that they can stay stationary under compressive load. Right. So the constitutive law, again, this word constitutive law, if you're doing continuum mechanics, you will learn about it. But what it means is, it relates the shear stress, which is defined as the shear force, to the surface area over which the force is acting. So this, if it was a square cross section, then this would be A. So the shear stress results in a continuous change in the angle theta, and viscosity is what tells us what will be the amount of that d theta by dt for a given tau. Okay, so this is called constitutive. This links the force with the resultant deformation. And this d theta by dt is also called the strain rate or the rate of strain. Okay. And geometrically, we can show that this rate of strain d theta by dt, which is a change in the angle. So this angle is this theta, is for fluids is actually equal to du by dy. So earlier I had drawn a square. Now I'm drawing it as some fluid between two plates. Same idea. So y in this case is this direction, that is um, perpendicular to um, the direction of shear force, and u is the direction of flow in the direction of shear force. So the shear force results in a flow of fluid. Let's say this is called u as a function of y, in the sense that you will see that some sort of profile will develop, and this we had discussed already, because the top plate is moving because of the shear force and the bottom plate is stationary. So it's the slope of this u as a function of y profile, um, that is what this du by dy is.
Excuse me, sir.
Yes,
So
please.
we say that the bottom plane which is stationary, but it may slip now. Like just above that, it may slip or not, or it be in a rest always.
So you
Like
mean the
ऊपर कहते
bottom plate is stationary or
नहीं
the
हम सर
fluid
लाइक
that is
बाय डिफॉल्ट
contacting it?
स्टेशनरी, लाइक जो नीचे वाला वो स्टेशनरी है, उसके ऊपर जस्ट पॉइंट होता है, उसको हम बोलते हैं कि वो स्टेशनरी है, वो जीरो पे रहेगा, उसके बाद स्पीड बढ़ती रहती है जैसे ऊपर ऊपर जाते हैं सर। वैसे
Right.
ही जो नीचे वाला पॉइंट है वो नीचे स्लिप भी हो सकता है ना, इसको अपने बोलते हैं स्टेशनरी।
Okay, okay. So very good. I mean, your question is, why is the fluid particle that is contacting the bottom plate stationary?
यस इट मे स्लिप।
Right. Very good. So let's then go to that point, which is called the idea of no slip. That was exactly what the next discussion point was. Okay, so we call it the no slip condition. It's a very common terminology in fluid mechanics. So what this says is that whenever you have a fluid particle contacting a solid, then the fluid particle is if it flows with the same velocity as the solid. So basically there's no relative velocity between the fluid and the solid. And the reason it happens is because you have these tiny undulations on the surface. I mean, see, mechanically you can never have a completely smooth surface. You'll have some sort of roughness. So if you microscopically look at this part, then what you see is that it is indeed it is actually having some sort of undulations. You can reduce them by using a sandpaper or some abrasive to make it you can buff it to make it as smooth as possible, but microscopically you'll always have some undulation. And we're talking about fluid molecules. The size of a molecule is of the order of 10 to the minus 10 meters. These undulations that you will get will definitely be larger than that. You won't have undulations, you won't have smoothness of the size of an atom. So what happens is these fluid molecules, if I just zoom into it here, then these tiny fluid molecules, you can have, let's exaggerate here. So this is the surface. let's say this size is of the order of 10 to the minus 6 meters. It's quite a smooth surface, 1 micron roughness. And then you're talking about molecules which are 10 to the minus 10 meters. It's 1000 10,000 times smaller. So you can have lots of molecules here. So of course, I mean, these undulations will stop those molecules. So that is what results in the relative speed between the solid and the fluid becoming zero. And no matter how, and people did the experiments, they tried to make it much more smoother. Even then, they saw that this is what the situation was. So that is the reason. Practically, also, we notice that there is a zero relative velocity between the solid and the fluid, and this is what we call the no slip condition.
Okay, sir. Thank you.
Good. Right. So viscosity, right? So we just talked about the constitutive law for fluids, which is what relates the shear stress to the rate of strain or the strain rate with the constant or the constitutive constant called viscosity. And it's called constitutive law because it it has the parameter mu in it, which is dependent on the constitution of the material, what it constitutes. So if it's a highly viscous material, then you will have a larger mu, which basically means that for the same shear stress, you will get a smaller change in strain rate. Okay, so smaller, not change in strain rate, smaller strain rate. That is smaller change in theta with time. Now this viscosity mu is generally a strong function of temperature. And the reason that is very important for us is because we would want to solve problems. And while solving problems, most probably we'll be dealing with the situation where the temperature may also be changing in fluid mechanics. So we should not be using the viscosity value for a different temperature. We should be using the viscosity value corresponding to the same temperature. In fact, I have a plot between the dynamic viscosity mu versus temperature in degree centigrade for air in this case. Okay, so the blue diagram is for dynamic viscosity mu. Kinematic is simply dividing that by the density of the fluid. So you can see that let's look at the value at 0 degrees, which is somewhere at just below 20 micropascal second. And then if you go to, let's say, 300, then you are at 30. Okay. So there is a significant change. There's more than 50% change in the viscosity. Now 50% change is significant. I mean, if you are multiplying this in a relation, then the error that you may get is of the order of 50% or more. So one has to be very careful when this is air, of course, and different materials will have different change in viscosity with temperature. But in general, the viscosity is a strong function of temperature. So one has to be very careful about that when solving problems. And for in terms of pressure, because again we'll be dealing with different pressure values, viscosity is quite a weak function of pressure. So then we don't have to worry in terms of what pressure we are applying. We can simply use the value at atmospheric pressure, unless you are at, for example, for water, if you are beyond 50 atmospheres, only then you see some sort of appreciable change in volume of the water. Otherwise, the compressibility of water is all. I mean, sorry, what I'm saying. Otherwise, the viscosity change in water also is quite negligible for large temperatures. Right. Now, another very important idea that is related to the definition of fluid is the idea of layering. Or the word laminas. You may have heard the word laminar flow. Okay. If you haven't, that's okay. You'll hear it a lot. So the idea of layers is very important. As we have just discussed above, or we have been talking about, you can see these blue layers. So the bottom, the red point is where the fluid is stationary, and then as you move up, you see that the layers have gradually they increase their x velocity. So this idea of layering in fluids is very important. So in general, for when the speed of flow is not above some critical point, then the fluid will flow in layers. And you can again look at Van Dyck's book for those pictures, where you can indeed see that the fluid flows in layers. Those layers can actually be visualized through flow visualization phenomena. But there is something interesting that's happening. So when the fluid is flowing, it is through these layers. These layers actually talk to each other. This talk has to be put in double quotes. They don't literally talk to each other, but they communicate, or there is some information transfer between them. And this talking happens through viscosity. So let's understand that from a molecular level. Let's understand the mechanism of what's happening here. So let's look at one layer. Let's say sorry for that. So let's just look at the bottom layer, which is let's say stationary, and the one above it is moving. It's a continuous change, but let us say that the layer above it is moving with some velocity and the one below it is stationary. So this we are talking about the bulk velocity, but molecules always have some Brownian motion. So what that means is if you have a molecule, whatever its bulk velocity is, it will always have some sort of random motion. So it will not stay stationary. The fluid molecule will, even a solid will, they'll keep juggling around with some in all directions. That's called Brownian motion. That is what causes diffusion, for example. So if you have a fluid molecule, it will have some Brownian motion. So what happens is, let's say these layers in the molecules in the top layer, they are the bulk flow is from left to right, but there is also some Brownian motion. So what happens is, because of this Brownian motion, once in a while, this molecule from top will jump to the bottom layer, right? And vice versa, molecules from the bottom layer, once in a while, will jump to the top layer. But they have different momenta. The one at the bottom was stationary in the sense of no bulk velocity in the x direction, and the one on the top was moving. But since the top one jumped at the bottom, so what it did was, it's like a car moving in a fast speed, and then it enters a lane where the cars are stationary. So it will hit the car and some sort of apply some sort of momentum. Whereas if a bottom molecule which was stationary, the stationary car, suddenly you put a stationary car in a fast moving lane, the other cars will hit. So everything will slow down. So this is how they create some sort of shear force over each other. So a faster car will enter a slower lane and tend to increase its momentum, and the one which is moving at the slower lane, because of the Brownian jump, it will slow down the top layer, so it will apply an opposite force and slow it down. Okay. And this concept of viscosity actually is because of this microscale phenomena. Viscosity is not a microscale property as such. It is just a macroscale property that we notice because of this microscale phenomena that we have just discussed. But as engineers, again, we don't worry about the microscale. I mean, if you were studying statistical mechanics, there is where you'll talk about how to calculate viscosity from first principles, from the molecular nature of the materials. But engineering wise, we measure them using rheometers rather than actually using first principles. But one should, as As a science student, you should know that what is the molecular origin of this phenomena called viscosity. This is the reason there is nothing like an ideal fluid, because every fluid will have some Brownian motion that results in these layers talking to each other, or these layers applying shear stress on each other, or these layers um, uh, exchanging momenta between each other. Right? Any questions on that?
No, sir.
Let's now look at layers in fluids that we just talked about. So here's a picture from Van Dyke where you have a fluid flowing from left to right. So you can see on the top it's all nice and straight, and then there is some sort of cavity which where what the fluid does is, let me open it so that I can write on this as well. Yeah. So I'll use red color. So you can see that on the top, the streamlines, so these are basically flow visualization. So what you've done is you have captured, you have put some sort of tracer particles and then taken a long exposure so you can see the particle moving, and that results in a path line of the fluid. So in the top you can see that the fluid particles are moving, the fluid is moving in almost horizontal, but at the bottom what happens is there is some fluid filling in this cavity, and then the top fluid, it applies some sort of shear, and the fluid which is in the cavity, at the bottom it is stationary, at the top you move it. So what happens is since the fluid cannot go out, there's a cavity, so it starts circulating to ensure that these boundary conditions on the fluid are respected. So the top fluid will start getting a shear and then sort of takes this kind of a path and it starts rotating. Okay, so this is what happens because of the viscosity in the fluid. Now if hypothetically you had a fluid which had zero viscosity, so that means this hypothetical fluid, the layers cannot talk to each other. So if I move one layer, the other layer will not see any effect, and that is where your strain rate will not develop. Okay, but these are all theoretical ideas. In reality, it never happens because you cannot have a zero viscosity. So we'll not talk about those. But a physicist who was talking about these theoretical ideas may want to discuss what happens in an ideal fluid from the strain rate point of view. Okay, so this is just a starting of the course. I don't want to go any deeper than this. Just want you to understand some concepts related to viscosity. Another related idea is called boundary layers, a boundary layer. So boundary layers are again imaginary layers that develop over a solid surface. So let's say you have a flow happening, you had a uniform flow. So that is how I'll denote it. So uniform means there is no change in the flow speed with height, with the y direction. Because right now the flow did not encounter this solid surface. And then what you've done is you've put a solid surface, and the fluid now is flowing above it. So again, because of this no slip condition that we've talked about, the fluid molecules which will be touching the surface will have now a 0x velocity, and the one on the top will have almost no effect from the solid. So we see a profile that will develop, a velocity profile, which is some sort of drawing a parabolic kind of a profile. We will in this course, from theoretical ideas, we will derive the form of these profiles, or at least discuss them. So this is u as a function of y. U denotes the flow in the x direction, flow speed, sorry, flow velocity component. Now what we'll see is that theoretically, now if this was, let's say, u infinity, theoretically the x velocity component over the plate will never reach u infinity. It will asymptote towards it, but it will never reach that. But practically what we say is that the point where the flow speed becomes 99%, that's 0.99 of u infinity, that is the edge of the boundary layer. Okay. Now what is the meaning of that? So the meaning of that is that within the boundary layer, that is in the region below this, the fluid sees the plate. We say the fluid can, again in double quotes, see the plate, because the fluid velocity was modified. But beyond this, in this region, fluid has, or let's say not fluid, the flow should we say flow? Because above, in the above region, outside the boundary layer, the flow has not seen the plate at all. It's almost flowing with the same velocity. Okay. But within the boundary layer, the flow speed has changed. Okay. So we when we'll be solving problems and when we'll be analyzing flow, we'll be analyzing it in two parts. One is inside the boundary layer, and one is outside the boundary layer. And if you were to now draw a locus of all the because I can draw a boundary layer here as well. So here I will see that this 0.99 of u infinity will be reaching a bit earlier. So if I join, if I take the locus of all these points, then I'll get something like this as my boundary layer. So this is my boundary layer. And we'll discuss all these, don't worry about that. So the region inside the boundary layer is typically called a viscous flow. I mean, it doesn't mean that the fluid does not have velocity. It's just that the effects of viscosity are seen inside the boundary layer region, and outside the boundary layer we call non-viscous flow. Just terminologies. We'll have many lectures on this idea, and then we'll also talk how to mathematically model the flow equations inside the boundary layer as well as for the outside boundary layer region. In fact, two completely different theories have developed to deal with the flow inside and outside the boundary layer region. But that's all we'll talk about it for now. So I mean, if there's anyone who's not clear about the idea of a boundary layer, you can ask, I can explain again.
So, how do we know that what is U infinity?
Now that's known. So you have created this initial flow using, let's say, a fan. So you would know what sort of initial uniform flow that is being created. Or the other way is, I mean, see, these are approximations. So this plate could be a car, and the car is moving in a stationary fluid. So that U infinity basically becomes the speed of the car.
Okay, sir.
Okay, so these are all real life phenomena. It's not some hypothetical experiment that we're doing. So this idea of boundary layer, it becomes prominent in external flows. That is, flows where bodies are moving in free fluid. So if you have a submarine moving in water, with a speed of let's say 15 meters per second, then you can analyze the problem as a stationary submarine with water flowing at 15 meters per second across it. Okay, good. So let's move on to our next idea for today. So this was all under the topic of what are fluids and the idea of viscosity. The next is complex fluids. So let's take the shear stress tau versus d theta by dt behavior. Now, I already gave you a relation where tau was mu times d theta by dt. Okay. So we assumed a linear relationship between tau and d theta by dt. So what we have for a constant mu value, you get a line like this. So these fluids are called linear fluids, also called Newtonian fluids. Right, and that's good. I mean, air and water both are Newtonian in nature. So most of the fluids that exist in our world can be analyzed using this constitutive law, which is tau equals a constant mu times d theta by dt. But of course, all fluids do not show this behavior. So let's briefly talk about what sort of options we have available in terms of the behavior between a relationship between shear stress and strain rate. We have fluids which show this kind of a behavior. Okay, so what this means is up to some tau naught there is no flow. So flow basically is d theta by dt. So you can think of it as a jelly. Now if you take a jelly, it's like a solid. So if you apply a shear stress, a slight shear stress, and leave it, it will come back. But if your shear stress goes beyond a certain value, let's say tau naught, then the jelly will flow. So these fluids are called Bingham fluids. Bingham's name of the person who figured out this phenomena. So again, these are some special kind of fluids, and they fall under the category of complex fluids. Now, another types of fluids, let's say where the slope will increase as your rate of strain increases. So they are called shear thickening. Thickening in the sense of becoming more viscous, because viscosity is nothing but the slope of this line. So as your rate of strain increases, the viscosity increases. A very classic example of this is cornstarch mixed with water. If you haven't seen those videos where people walk on fluids, you should definitely see that. Just YouTube walking on cornstarch, or walking on shear thickening fluid, or walking on fluid. So these materials, for smaller values of strain rates, I mean, if you try to walk slowly, okay, so what happens is the strain rates are quite low, and it's very sort of non-viscous. So you will you will sink. It's very fluid. But if you try to walk a bit faster, your rate of strain is very high. It becomes highly viscous. You literally walk on it, becomes very hard. So that's the idea of shear thickening. These materials, they will become more viscous as you increase the rate of strain. And then you also have materials which are shear thinning. Toothpaste, for example, if you try to, I mean, you have learned over time how to ooze out toothpaste, but if you try to assume, if you were if you give it to someone who's used to Newtonian fluids, they will press it and assume that uh, the uh, the rate of strain will be proportional to tau, but that is not the case. Sometimes it suddenly comes out. That's because as you increase the strain rate, its viscosity is decreasing. So one has to learn from that and then reduce the strain rate as you start as the fluid starts coming out. Okay, so their viscosity will decrease as you increase the rate of strain. Right? Any questions? Right. Very good. So moving on to the next idea. Flow visualization. How do we visualize flow? So the methods of flow visualizations have been quite intuitive in the past, and they're still used. So you visualize flow using smoke. Smoke is particles of carbon. So what happens is if you have gas airflow happening which is transparent, but if you introduce smoke into it, what will happen is you will be able to see the particles depending on how they are flowing with the fluid, and then you can take a camera and picture it. So this will help you figure out the trajectories of gas particles. Then the other one is for fluids or liquids, you have dye. So if you have water flowing in a laminar flow, you can't see it unless it becomes turbulent. You can't see it. And then if you introduce a dye particle, then you'll be able to see it. So I'll send you some videos where experiments have been conducted many years ago, where people have captured the nice parabolic profile, the boundary layer profile, or the shear layer profile over solids by introducing dye into the liquid. Okay. Then you can introduce bubbles. For very small bubbles, if you introduce them into a fluid, they'll tend to flow with the fluid. Of course, they'll have some net upward velocity as well. But for very large flow speeds, that upward velocity becomes very small because of the buoyancy of bubble. Bubble wants to rise up. But if you have a very strong flow speed, then that upward velocity becomes negligible. So the bubbles will tend to flow with the fluid, with the liquid in which it is immersed. So you can use these bubbles to get some idea of what is the direction of flow. You can use powders. So if you have a gas, again you have very light powder in very small size particles, very light particles of powder in a strong flow. Then the powder will tend to flow, and then you can visualize. You can take light from one side and the camera from the other side. Then the powder will sort of reflect light, and then you can see those powders, and hence you can figure out what is the uh, flow profile of the fluid. Okay, so these are some techniques. The other is, for example, in a river, if you want to figure out what is the flow happening, if there's some circulation happening, you can put some neutrally buoyant particle. So that means some solid body which has an overall density which is the same as fluid density. It could be a cork particle, it could be some plastic that you have made in such a way so that its net density is the same as the fluid density. So it has some air in it and so on. We call it neutrally buoyant. Then you can use the idea of shadowgraphy. I sent you a short video last evening over the chat group on shadowgraphy. Shadowgraphy is a technique where we exploit the idea that the refractive index of a gas is a function of its density. Refractive index is a function of density. Now, when the flow happens for fluids where the density changes, even slight density changes can be captured using the imaging techniques, as you saw in the video where the refractive index was changing, and hence you could see the bubble, the gas plume in a flame, and so on. Okay, so these the other is interferometry, again using the idea of refractive index changes with density. So it is an indirect way of measurement. You're not measuring the flow speed directly by putting a particle there, like in smoke, dye, bubbles, or powder, but in fact you are seeing the change in another property, refractive index, because of the change in density, which results as a flow effect. And there are many sensors available that you can use which work on different principles to measure these flow phenomena. Okay, so this is called flow visualization. There's a complete course called Experimental Methods in Fluid Mechanics, where you learn about these flow visualization techniques in detail. So I'll not speak any further about this, but it's very interesting. If you enjoy this course, then you should definitely take up that course in Experimental Methods on Fluid Mechanics. Now we talk about flow visualization, but what exactly are we measuring? What do we want to get out? So how do we quantify the complete nature of a flow? So we would want to figure out the velocity field, that is the velocity, all components of velocity at all spatial points at all times. If I have a pipe, then I would want to know the all the components of flow velocity at all points in the pipe at all times. You can take lots of pictures. Each picture corresponds to a particular snapshot in time, and this picture is covering the complete domain, so the complete pipe region. So you can get lots of these pictures and then make a movie out of it. So that becomes your velocity field. Field basically means that you have the information over all points in space. Then you would also want to capture the pressure field. And then if you were talking about energy ideas, then we want to have the temperature field as well. But in this course, we'll not be interested in the temperature field. That will come up in the next year in the course on heat transfer. So this course is about velocity and pressure, and the next course on heat transfer will be about temperature in addition to velocity and pressure. So basically, if you figured out the velocity, pressure, and temperature fields in a fluid, you have measured everything that you can. There's nothing else to measure in a flow. Right. So flow visualization is an experimental technique that helps us measure these. Now, the theoretical ideas that we develop, they will result in differential equations where the unknowns, because an equation has an unknown that we call the dependent variable, and the unknowns will be velocity field, pressure, and temperature. Now this will come in heat transfer, and this is in fluid mechanics. So we'll be solving for the unknowns, the velocity field and pressure. So velocity field will ultimately mean your u, v, and w scalars. So let's call it v. That's more common. The velocity field. All right. Right. The last idea for this discussion before we jump into the course is the idea of Lagrangian versus Eulerian. It's very confusing for many of us. Now, if you're doing a course in continuum mechanics, you will formally be studying these ideas, and in fact, you will be talking about the equations of conservation of mass, momentum, and energy from both perspectives. So that course will give you a deeper picture into the theoretical ideas of these two concepts and how to go from one form to the other, as I discussed earlier. So Lagrangian is uh, is the idea of dealing with flow equations where you look at some particle. And the reason this concept is easy to apply is because the Newton's second law, which is force equals mass times acceleration. This law is valid if you are dealing with a particular particle or a particular mass. You take a particular mass, even though the mass is moving, that's okay. So for that collection of particles, which we'll call a mass, you'll find the net force acting on it, and then that will result in a net acceleration of the mass. So you can apply the Newton's second law of motion um, in this Lagrangian concept. It's very simple, it's easy to apply, it's intuitive. But for the Eulerian approach, and that is the approach we actually take in fluids. So this Lagrangian approach is more common in solids, although you can apply it in fluids as well. The Eulerian approach, what we are interested in is not a fluid particle, because see, in a pipe the flow is happening from left to right, then new particles will keep entering. You can't track a particle or a collection of particles that you call a mass. You would rather want to study what's happening in a spatial volume that we call a control volume. So although new particles are entering and the old ones are leaving, you still want to figure out what's happening in a control volume. So to write the differential equations to write the relation that relate force and acceleration for particles inside a control volume, you cannot simply apply Newton's second law here. You have to apply Newton's second law using the Lagrangian approach and then transform that to some sort of Eulerian approach. Okay, so this is more complex in the sense of how you apply them mathematically, but they're interchangeable. Physics is still the same. It's the Newton's second law applied in both cases. Right. So we'll stop here now. That's the end of the discussion on ideas on fluid mechanics. And from the next lecture, we'll start discussing the topics of this course. The first one would be fluid statics in the next one lecture, and then we'll move on to the dynamics of flows. I gave you a couple of problems from Irido, 3 of those. Please do try them. If anybody has any questions, you can always ask me after the lecture or over email or other things. I'll stop recording the lecture now. If anybody has a question, feel free to ask.
I had a question from this. I heard of I